Good afternoon to all of you. Today topic of my presentation is echo calculation. Echo calculation is based on two-dimension measurement in TE and along with Doppler data. So we will see them one by one. First we will see what is Doppler measurement and what is the principle behind Doppler. So the Doppler effect is first described by Christian Doppler in 1842. While studying the movement of the star, he found that there is a shift in frequency when acoustic source is motion compared to stationary observer. So similarly, when car is come toward us with blowing horn, the horn frequency is same, but when car coming toward us, the frequency is increased. You can see high pitch sound. But similarly, when car goes away from you, you can see reduced pitch sound from the car. So it is the frequency shift. Similarly, when we hear Doppler signal from the red blood cell or tissue, when echo received toward the transducer, we hear high frequency as compared to the blood or tissue moving away from the probe. So here transmitted and received frequency will not be the same, and you can calculate this frequency shift by subtracting transmitted frequency from received frequency. So if this result is positive, then the movement is toward the probe, and if this result is negative, this frequency shift is negative, then it is movement away from the probe. So this frequency shift determines relative velocity and flow of the blood or moving tissue, and this effect is known as Doppler effect. Now this is the Doppler frequency shift equation. Here target velocity is equal to speed of the sound in the tissue multiplied by frequency shift divided by twice into frequency of emitted ultrasound along with angle cos theta. So cos theta is the angle between ultrasound beam and target velocity. So this flow velocity is most accurate when beam is either parallel or anti-parallel. So angle should be at 0. So at 0 degree angle you can measure actual velocity. And when this angle is increased, suppose as you see in this image, at the 0 degree angle the velocity is 2 meter per second, but if measuring angle increased to 10 degree, then the velocity measured is 1.97 meter per second. Similarly, it increased to 30 degree, then the velocity will be 1.73 meter per second. At the 60 degree, you can measure half of the actual velocity, and at the 19 degree, you can measure 0 Doppler shift. So diversion up to 20 degree can be tolerated with error of less than 6%. Now use of Doppler in ultrasound is to evaluate and quantify blood flow. Here transducer is a source and receiver, and flow is motion relative to the transducer. Flow coming toward the transducer is above the baseline, and flow below the transducer, flow going away from the transducer will be below the baseline. And this is a spectral waveform representation of the Doppler signal. So you can measure direction of the flow, velocity like VTI, maximum and mean velocity, and based on this you can calculate stroke volume from Doppler signal. You can identify quality of flow, whether it is normal flow or abnormal flow. And applying continuity equation, which is a law of conservation of mass, and Bernoulli equation, you can calculate wall area and measure pressure gradient across any narrowing or regurgitation. So calculation based on this Doppler equation are 4 types. First is the volumetric measurement. In volumetric measurement, you can calculate stroke volume, cardiac output, QP by QS ratio, and regurgitant volume and regurgitant fraction. And second type of measurement is the pressure gradient. Here you apply Bernoulli equation on Doppler data, and you can get maximum gradient or minimum gradient. Third type of data you can get from the Doppler equation is the wall area. You can measure stenotic wall area and effective regurgitant orifice area by applying continuity equation and Pizza equation. Similarly, fourth type of data you get is the intracardiac and pulmonary artery pressure. Here you have to apply Bernoulli equation on Doppler data, and these are the equation you can apply, and you can get the RVSP, PA pressure, and all possible intracardiac pressures. Now we will see first volumetric measurement. Volumetric measurement and velocity is a different term. So do not confuse between blood flow velocity and volumetric flow. Blood flow velocity is the speed at which blood flow in the vessels. It is expressed as a centimeter per second. While the volumetric flow, it is also known as a stroke volume. It is the amount of blood that flow, and it is expressed as a cubic centimeter per second. So the equation for the volumetric flow is the velocity of the blood flow multiplied by cross-sectional area. So to measure this volumetric flow, you have to measure Doppler measurement of instantaneous blood flow velocity, and simultaneously you have to measure cross-sectional area in the 2D echocardiography. Now this stroke volume, which is a volume of blood that propagates during each cycle, is measured with this measurement of the volumetric flow. Here acceleration and deceleration of blood flow velocity during the ejection period produce distinctive Doppler profile. As you see in this image, there is a velocity profile is produced, and this measurement of this velocity profile is called velocity time integral. It is the summation of the entire flow period, and it is expressed in centimeter. Here VTI is the distance of that blood travels with each heartbeat. It is also called as a stroke distance. It is the red cell distance with red cell travel during systolic ejection phase. When you multiply VTI with a cross-sectional area of conduit of measurement like mitral valve, across mitral valve or across alveoli, you obtain volumetric flow or stroke volume. And when you multiply this stroke volume with heart rate, you can get cardiac output measurement. So when blood is forced through a narrow opening, this laminar flow is replaced with turbulence. Generally, there are three types of flow. First is, as you see in this LVOT, there is a flat profile or laminar flow. So each part of the flow have equal velocity. When this flat laminar flow going in the ascending aorta, it is converted in the parabolic profile. Here the most center part has higher velocity and peripheral part has a lower velocity. Third type of flow is a turbulent flow, which is when the blood passes through narrow orifice, the laminar flow will converted into turbulent profile. So to measure stroke volume and cardiac output, you have to measure this flat or laminar flow. So the stroke volume and cardiac output are best measured with TOE at the two positions. One is the LVOT and other is aortic valve. The advantage of the measuring at LVOT and aortic valve are acceleration of blood through LVOT and aortic valve during systole favors laminar flow with the flat profile of velocity, in contrast to parabolic flow velocity in the ascending aorta or pulmonary artery. Second advantage is that here entire ejected stroke volume travels through this structure as compared to the peripheral structure. And third is the LVOT and aortic valve is more circular as compared to mitral and other valve, and cross-sectional area change minimal during cardiac cycle. So to measure cross-sectional area of LVOT and aortic valve, you have to use mid-esophagus long axis, aortic valve long axis view, and TE provide excellent view of this LVOT and aortic valve. For the aortic valve, the cross-sectional area will change during systole but remain circular during mid-systole. So you have to measure during mid-systole. So measurement of VTI and cross-sectional area should be done in the same anatomical location. So as per this equation of cross-sectional area for the LVOT or aortic valve, it is multiplied by with pi and radius square. So to simplify the equation, radius is replaced with the diameter by 2, and for the simplest equation is the 0.785 into diameter square for any cross-sectional area. Similarly, you can measure cross-sectional area of mitral valve, but mitral valve orifice is not circular and its size changes during diastole. So you have to take two diameter, one is the antero-posterior diameter and other circular diameter. So here you have to take pi into d1 into d2 square. So the diameter 1 is the diameter of mitral valve in mid-esophagus for chamber view, and diameter 2 is the diameter of mitral valve in mid-esophagus long axis view. So after calculating cross-sectional area, you have to calculate VTI. For the VTI of the LVOT, you have to take pulse wave Doppler across aortic wall and just 1 centimeter proximal to the aortic wall in deep transgastric long axis view or deep transgastric long axis view. You can measure LVOT VTI. Similarly, you can measure simultaneously both LVOT and aortic wall velocity, and as you see in the image, you get double envelope profile. Now to measure stroke volume of aortic wall and mitral wall, you have to measure VTI. VTI of aortic wall is similarly measured across in deep transgastric long axis or transgastric long axis view. So you have to measure by applying continuous wave Doppler or pulse wave Doppler. And for VTI across mitral wall, you have to measure in the fourth chamber, and you have to profile both E and A wave in mid esophagus fourth chamber view. So after measuring VTI, you have to multiply it with cross sectional area, and you get stroke volume across aortic wall or mitral wall. So on the right side, you can also measure stroke volume across pulmonary artery and RVOT. So to measure cross sectional area and VTI for the pulmonary artery and RVOT, you have to measure it in RV inflow outflow view or transgastric view with angle of 110 to 150. So to measure the RVOT velocity, you have to put pulse wave Doppler 1 centimeter proximal to the pulmonary wall, and for the pulmonary artery, you have to measure at the level of pulmonary wall with continuous wave Doppler. So after measuring, you have to measure cross sectional area and VTI in the same image, so to avoid any error. So after measuring cross sectional area and VTI, you will get stroke volume across RVOT and pulmonary artery. Now based on this, you can calculate pulmonary to systolic flow ratio. QP/QS is usually indicate the magnitude of shunt. So here you have to measure pulmonary blood flow or pulmonary stroke volume and take ratio of along with aortic wall stroke volume. So the equation is QP/QS is equal to stroke volume across pulmonary wall into heart rate and stroke divided by stroke volume across LVOT divided by heart rate. You can also take stroke volume across aortic wall. So to simplifying this equation, heart rate is removed, and the final equation is stroke volume across pulmonary wall divided by stroke volume across LVOT. So here there are two variables, pulmonary stroke volume and systemic stroke volume are involved. So if any error in measurement of this data, the error will be compounded. Simultaneously, there is a AR or PR. So with AR and PR, this data is QP, you calculate will underestimate actual QP/QS. Now after QP/QS, you can measure regurgitant volume and regurgitant fractions with this volumetric data. So regurgitant volume is the volume of blood that flow backward through regurgitant valve during one cardiac cycle. For a regurgitant valve, so any regurgitant valve eject not only stroke volume but also regurgitant volume. So you have to measure two valve stroke volume, one is the normal valve and one is the regurgitant valve. So to measure regurgitant volume, you have to subtract normal stroke volume through normal valve from the regurgitant valve. Like to measure regurgitant volume across mitral valve, you have to subtract stroke volume from LVOT from stroke volume from mitral valve. Similarly, to measure regurgitation volume across aortic valve, you have to measure stroke volume across regurgitant valve like aortic valve or LVOT and subtract it from the stroke volume across mitral valve. So the regurgitant valve has the total stroke volume which is equal to regurgitant volume plus stroke volume delivered to the peripheral circulation. So by applying this equation, you can measure regurgitant volume, and regurgitant volume on getting this regurgitant volume, you can get regurgitant fraction. It is the percentage of total stroke volume that regurgitate through incompetent valve. Other two methods are Pisa method and continuity equation. So here mitral valve inflow stroke volume measurement is little bit difficult, and because mitral valve is elliptical and it changes its shape during diastole, so it is little difficult. And if there is a regurgitation of reference valve, like if MR with AR, then you cannot measure exact values. So one valve should be competent to measure this regurgitant volume. Now after this volumetric data, you can measure valve area through applying Doppler measurement. So in addition of 2D planimetry, spectral Doppler measure valve area by 3 methods. First is the continuity equation. It is a law based on law of conservation of mass. Second is Pisa method, and third is a pressure half time. Pisa method is also apply continuity equation. So both are similar, but pressure half time is based on pressure data. So continuity equation state that the volume of blood passes through one side, like LVOT, is equal to the mass of or volume of blood passing through another side, which means what comes in must come out. So it is based on volumetric data. So here volumetric flow at one side, like as you see in the image at the LVOT, is similar to the volumetric data at another side, like aortic valve. So if you know, as you see in the image, if you know LVOT velocity or VTI and cross sectional area, and similarly peak velocity across aortic valve, stenotic aortic valve, then you can calculate aortic valve area by applying continuity equation. This continuity equation is theoretically independent of transvalvular pressure gradient, because there is no gradient in any calculation, so it will not affect with the high gradient or low gradient. Similarly, it is not affected by LV compliance, while other method affected by LV compliance, changing LV compliance. Third is a changing hemodynamic conditions such as increase in forward flow that occurs during exercise will not affect this on this continuity. If flow is increased and then flow will increase in both the valve area, so it will not affect measurement by continuity equation. And third, the limitation is that continuity equation, it does not apply in circumference of regurgitation in the reference valve, because if the reference valve is regurgitated, then you cannot measure actual volumetric flow. So it will not apply. If other valve, reference valve is regurgitated, then you cannot use this equation. Second method of valve measurement is a Pisa method. It is a short form of proximal velocity isovelocity surface area method. So Pisa method applied the continuity principle in color flow Doppler mapping in the region of mitral valve orifice. As you see in the image, when flow is converging from the LA or LV. Here velocity of blood flow increase when it approaches smaller orifice like stenotic valve, resulting in aliasing of the color flow signal and creation of there is a shell like proximal flow convergence shell. So this Pisa radius or the change in color of or first aliasing velocity shell measured from the tip of mitral valve leaflet. So you measure this aliasing shell by measuring distance from the tip of mitral valve to the first aliasing color change. So by measuring this radius, you can measure Pisa radius or Pisa cross sectional area by applying in equation pi r square. So you know the radius of the Pisa, and you can measure cross sectional area of Pisa hemisphere. So after getting this Pisa hemisphere cross sectional area, you can get volumetric data at the level of Pisa radius by calculating product of the surface area of the hemisphere and aliasing velocity, which is generally taken as a 40 centimeter per second. So Pisa flow rate is calculated through this equation. Now Pisa method apply continuity equation. So the Pisa flow is equal to mitral regurgitation jet flow, or the flow rate at the level of regurgitation. So you measure velocity, highest velocity across mitral valve by applying continuous wave Doppler, and you know Pisa flow. So you can calculate effective regurgitant orifice area by dividing maximum velocity from regurgitant flow, and you based on this you can get EROA, and when you multiply this EROA with velocity across mitral valve, then you get regurgitant volume. So if this velocity and this area is less than 0.2, then it is a mild, and if between 0.2 to 0.39, it is moderate regurgitation, and if this EROA is more than 0.4, then there is a severe regurgitation. So this PISA method has certain limitations, like calculation of valve area based on PISA method is very time consuming, and you have to take continuous wave data, and PISA radius must be obtained at the same point in cardiac cycle, otherwise the data you get error in the data. So PISA method is calculated from a single frame image, so the overestimation occur if the jet is not holosystolic. Another important point is eccentric jet you cannot measure with PISA method because of angulation and inability to record maximum velocity. Similarly, PISA method has some advantage, like it is useful when 2D planimetry is technically limited, and when the continuity equation cannot apply with the use of regurgitant reference volumetric flow, and when PST method is affected by hemodynamic changes. So its accuracy is not affected by regurgitance of other valve, so you can use in that condition. Third method to measure valve area is pressure half time. Pressure half time is the time required for the peak transvalvular pressure gradient to decrease by 50%. So PST pressure half time, which is short form of PST. PST used to estimate the area of stenotic mitral valve using empirically determined constant of 220. So this formula is given by Hartley and also known as Hartley formula. So based on this you can measure pressure half time, and based on pressure half time you can calculate mitral valve area. Here principle is that larger orifice has a shorter pressure half time because pressure can equalize more quickly. So this pressure pressure half time you can also calculate by calculating deceleration time. So deceleration time, when you multiply it with 0.29, you can get pressure half time. So this pressure half time method used to calculate mitral valve area in severe MS, and similarly it also used to calculate aortic regurgitation severity in case of severe AR. So when you measure pressure half time, there is certain limitation, like measurement obtained with pressure half time is influenced by hemodynamic factor and depend on the compliance of LA and LV. Similarly, diastolic dysfunction leads to overestimation of severity of stenotic mitral valve. When pressure half time is shortened when high SVR leads to overestimation of stenosis. So when there is a decrease in LV compliance and severe ARs, then there is a rapid rise in the LV diastolic pressure with a resultant shortening of the pressure half time, and you will get overestimation of the mitral valve area. And in mitral valvuloplasty, atrial septal defect, atrial tachycardia and restrictive cardiomyopathy, you cannot get actual pressure half time. Now after getting this valve area measurement, we can measure pressure gradient across stenotic and valve or regurgitation lesion by applying Doppler data with use of Bernoulli equation. The Bernoulli equation describes the relationship between the increase in blood flow velocity and pressure gradient across narrow orifice. So as blood flow across narrow orifice, blood flow velocity increase, and this increase in velocity is related to degree of narrowing. So as you can see in the image, the actual Bernoulli equation is very complex, and it is based on convection acceleration of flow along with viscous fraction, and there is a difference in velocity proximal and distal to the narrow orifice. So here when in our clinical practice, the flow acceleration is not exist during peak flow. So at the peak flow there is no flow acceleration and there is a steady flow. So you can ignore it. Similarly, viscous friction is contribute if orifice is less than 0.25 centimeter per square or long tubular lesion. So you can ignore also viscous friction. And third point is then you after ignoring flow acceleration and viscous friction, you get modified Bernoulli equation. It is delta P, or pressure drop across the narrow orifice, is equal to 4 times the velocity, proximal velocity, distal velocity minus proximal velocity. So in our clinically significant lesion, the proximal velocity is very less, so you can ignore it, and the simplified Bernoulli equation is delta P or pressure gradient is equal to 4 times the velocity, 4 times distal velocity. So by eliminating flow acceleration, viscous friction and proximal velocity, the simplified Bernoulli equation states that the pressure drop across the stenotic orifice is 4 times the square of the velocity of high velocity jet. So this Bernoulli equation is used to calculate pressure gradient across stenotic valve. So in prosthetic and dysfunctional valve, there is a significant flow acceleration and you can get error in measurement in this equation. Similarly, viscous friction, which is present with long and tubular obstruction, when you measure that with this Bernoulli equation, you get error in the result. Third is when velocity in the proximal part is V1 is higher than 1.5 meter per second, then by using simplified equation you are ignoring it and you get the overestimated pressure gradient. It is occur in subaortic obstruction, significant AR, and intracardiac shunt or high cardiac output state have a V1 velocity is more than 1.5 meter per second. Similarly, with higher hemogrit, it is increased viscous fraction and has increased viscosity, and you are ignoring it and you get underestimated pressure gradient. Similarly, in anemia and reduced viscosity, you get overestimation of pressure gradient. Now another important point to be discussed is the Doppler measurement of pressure gradient as compared to cath lab measurement of pressure gradient. So Doppler ecography measure instantaneous blood flow velocity and hence the maximum instantaneous pressure gradient. So we get maximum gradient in Doppler data. So mean gradient which we calculate from maximum gradient is very well correlated with simultaneous measurement by cardiac catheterization lab. But cardiac catheterization lab report peak to peak pressure gradient. So they measure both pressure different time. So they measure LVOT pressure and then aortic valve pressure, systemic pressure. So they get the catheterization lab report of peak to peak pressure gradient in ES, which is pressure difference between peak LV pressure and peak aortic pressure, which is slightly lower than Doppler measure instantaneous pressure. So the point is, as both the event occurs in different time, so this is not physiological measure. So when we the LVOT contraction and highest pressure is occur before before aortic peak aortic pressure. So you measure both both pressure at different point of time, while in Doppler you measure simultaneously. So the peak instantaneous gradient measured in Doppler is accurate estimation of true physiological maximum pressure gradient in aortic stenosis. Now fourth measurement you get from the Doppler data and echo 2D data is the intracardiac pressure measurement. So there is no echo technique that measures direct intracardiac pressure, but estimation of intracardiac pressure can be done from Doppler derived pressure gradient from regurgitant jet or shunt and a known proximal or distal chamber pressure. So here the step are: first you measure peak jet velocity by continuous wave Doppler, then peak you can get peak velocity to peak gradient by applying Bernoulli equation, then estimate the pressure, either you know originating chamber pressure or receiving chamber pressure, and then apply this Bernoulli equation and you can get measure originating chamber pressure or receiving chamber pressure. First we see RVSP or pulmonary artery systolic pressure measurement from TRZ. So the peak TR, as you see in the, you can measure TRZ or TRZ in mid-esophageal 4-chamber view or RV inflow outflow view. So this peak TR velocity, as you see in the image, it reflects systolic peak pressure gradient between RA and RV. Here RV is originating chamber or high pressure chamber and RA is low pressure. So the pressure gradient, as you apply Bernoulli equation, pressure gradient between RV to RA is equal to 4V square. So highest 4 times the highest velocity. So when you apply this equation, you get RVSP is equal to, or pulmonary artery systolic pressure is equal to 4 into V peak TR velocity plus RA pressure. So you can measure RA pressure or CVP with hemodynamic data, and by applying this equation you get RVSP. So this equation is not valid in case of severe RV dysfunction and VSD or severe PR. So you can also measure pulmonary artery systolic pressure from PDA shunt. Here you have to measure peak PDA velocity between aorta and PA. So this peak PDA velocity by continuous wave you get is reflect the systolic pressure gradient between high chamber pressure aorta and low chamber pressure PA. So when you apply this Bernoulli equation, you get systolic difference of systolic blood pressure minus pulmonary artery systolic pressure is equal to peak velocity across aorta and pulmonary artery. So you know systemic blood pressure by hemodynamic measurement. So you can calculate pulmonary artery systolic pressure by subtracting it from for peak velocity across aorta and PA. Third measurement of RVSP, you can also measure across VSD. So when you measure flow across VSD in the 4-chamber view or long axis view, the peak velocity VSD velocity reflects systolic peak pressure gradient between LV and RV. So when you apply this Bernoulli equation, the LV systolic pressure minus RV systolic pressure is equal to 4 times the velocity of peak VSD velocity across VSD. So LVSP is equal to systolic blood pressure. So you can measure RVSP by subtracting peak velocity from LV systolic pressure. Similarly, you can measure mean pulmonary artery pressure and pulmonary artery diastolic pressure from pulmonary regurgitation jet. So you can measure pulmonary regurgitation in upper esophageal pulmonary artery view or RV inflow outflow view. So as you see in the image, early peak PR diastolic velocity is the peak pressure gradient between PA and RV in diastole. So it is a measurement of mean pulmonary artery pressure. So high pressure chamber PA and low pressure chamber RV. So mean pulmonary artery pressure minus RV diastolic pressure is equal to peak velocity. For RVDP you can take RA pressure as a substitute, because in early diastole RV pressure and RA pressure are similar. So you can measure mean pulmonary artery pressure is equal to CVP plus 4 times the peak early peak PR velocity. Similarly, you can measure end PR velocity, and this end diastolic PR velocity reflects pressure gradient between pulmonary artery and RV at end diastole. So by apply, if there is no obstruction across tricuspid valve, then RV end diastolic pressure is equal to RA pressure or CVP. So you can get pulmonary artery diastolic pressure and mean pulmonary artery pressure by by measuring velocity of PR jet. Now based on you can also measure left arterial pressure from MR jet. So when you measure MR in 4-chamber mid-esophageal 4-chamber view, this peak MR velocity reflects the instantaneous systolic pressure gradient between LV and LA. And when you apply this Bernoulli equation, then as per equation, a high pressure chamber LV to the low chamber pressure gradient is equal to peak velocity. So LVSP is minus LA pressure is equal to 4 times peak velocity across mitral valve. So if there is no AS or LVOTO, then systolic blood pressure is equal to LVSP. So you can calculate LA pressure by this equation. Now you can also get LA pressure through, if there is a PFO, you can measure the gradient across the PFO by applying Bernoulli equation and subtract it from the if LA pressure is higher, then you have to subtract it from the RA, and if RA pressure is higher, then you have to measure it opposite side. Now you can also measure LV-EDP from ARZ. Similarly to the pulmonary mean pulmonary pressure or and pulmonary artery pressure, you can measure LV-EDP from ARZ. Here the end diastolic velocity is seen, in which we obtain in deep transgastric or long axis view, and the end diastolic AR velocity, which reflect pressure between the pressure gradient between aorta and LV. And when you apply this Bernoulli equation, you get diastolic blood pressure minus LV-EDP is equal to 4 times the velocity of AR and diastole. So LV-EDP is equal to diastolic blood pressure minus 4 times the velocity of end diastolic end velocity of ARZ. So at the end, this LV-EDP is equal to LAP, as at the end of diastole, mitral valve open and there is a no flow. So you can measure LA pressure through ARZ also. Now you are also measure. You can also measure SVR based on this Bernoulli equation. It is based on Ohm's law of hydraulic version. Here resistance or SVR is equal to pressure, as you see in the equation, delta P or pressure gradient across any ventricle divided by flow of or volumetric flow. So for the left side of heart or to measure SVR, we get atrioventricular valvular regurgitation jet velocity or velocity across MR. So there must be MR to measure this SVR. Similarly, the volumetric data we take is a VTI across LVOT. So SVR can be qualitatively determined from this measurement of flow and pressure and calculated by taking a ratio of velocity across mitral valve, peak velocity across mitral valve divided by VTI across LVOT. If this ratio you get data in 0.27 if this data is more than 0.27, this ratio, then it has 70% sensitivity and 77% specificity that the SVR is greater than 14 volts. And if this ratio is less than 2, then this data has a 92% sensitivity and 88% specificity that SVR is less than 10 volt. So to directly measure SVR in the wood, you have to use this equation as SVR is equal to 0.46 into plus 49.4 into velocity across MR jet and divided by VTI across LVOT. So normal SVR is 10 to 14 volts, and you get the the measurement through this echo data or Doppler data. Similarly, on the right side of the heart, you have to measure velocity across, there must be TR, and you have to measure PR by estimating calculating the ratio of tricuspid valve regurgitation peak velocity to the Doppler profile of RVOT or VTI across RVOT, and by applying this equation you can measure directly in the Wood unit. Now to measure measurement of contractility is also possible through Doppler data, and it is known as LV dP by dt. It is relatively load independent index of LV systolic performance. Here rate of pressure increase in LV during isovolumic contraction used to measure LV function. Because LA pressure does not change during isovolumic contraction, so velocity of MR jet reflects change in LV pressure. Here longer time interval indicates decreased LV compliance and decreased LV dP by dt, and it indicates the reduced systolic function. Now to measure this LV dP by dt, you have to acquire continuous trace of MR jet, and time then you have to measure time for velocity to rise from 1 meter per second to 3 meter per second, and you have to apply Bernoulli equation and measure pressure change from 1 meter per second to 3 meter per second. So this is the equation. You have to measure LV dP by dt is equal to 4 times into V2 minus V1 square. So dP by dt is, as in this equation, is 32 mm of Hg, and you have to divide it by time. So it is 1000 milliseconds. So you get the result. So normally its value is more than 1200, but if it is less than 1000, it is abnormal or reduced systolic function. Similarly, you can measure velocity in the right side of the heart. So you have to measure continuous data of the TRZ. Here you have to take time for velocity rise from 1 meter to 2 meter per second as compared to 1 meter to 3 meters per second in the left side. So by applying this equation, similarly you measure velocity or RV/dPP by dt, which is normally more than 1000 mm of Hg per second. Now, you can measure ventricular filling pressure by applying propagation velocity, and propagation velocity of a transmitral flow is measured from the mitral endoplane to 4 cm into LV cavity. Here you have to use simultaneously color Doppler and M mode. Here you have to measure the slope of early filling phase or E wave phase, which reflect the pressure difference between LA and LV along with differential compliance. So if this slope is more than 45 or vertical, then it is normal, and if slope is reduced to less than 25 cm per second, then it is a restrictive physiology, and it correlates with LV/dP of more than 15 mm of Hg. So when combine this peak transmitter, when you take the ratio of peak E velocity divided by velocity propagation and if the ratio is greater than 2, then it indicates elevated LV/dP. And you can also estimate pulmonary capillary wedge by applying tissue Doppler data. Tissue Doppler is a measurement of velocity of myocardial motion. Here high velocity signal of is filtered out, and you have to measure E prime and A prime along with continuous pulse wave data of E velocity and A velocity. And when you apply this in equation, like for the PCWP is equal to 1.24 into E/E prime ratio plus 1.91. So even you can take ratio of E/E prime and it indicate pulmonary capillary wedge pressure. So if the E/E prime ratio is greater than 10, it indicate pulmonary capillary wedge pressure more than 12 mm of Hg, and if ratio is more than 15, it indicate pulmonary capillary wedge pressure of more than 20 mm of Hg, and it is a predictor of mortality and morbidity in patient with LV dysfunction and MI. You can also get LA pressure measured by taking this ratio as E/E prime plus 4, and you get the LA pressure. So estimation of right side RA pressure is also possible by measuring tricuspid valve tissue Doppler imaging. So this is all the equation possible we can take easily during our 2D assessment of the in our patient. So thank you for the listening.